So James Gurney proposed the following problem. You have this Edward Hopper picture with this setup here, an open door, light coming in, and the question is, can the shape of the projected light be like this? So basically you have two quadrangles, one on this wall and one on the ground. Can this be right? And actually it can't, at least with the assumptions we naturally make when looking at the picture. And James showed it experimentally by making a cardboard setup and putting a light source to it. And you can also show it with a 3D setup, but you can actually prove it very simply with a little descriptive geometry diagram, and I wanted to show you the proof. So you can do a simple setup like this. Here you have in isometric projection the wall with the door and the adjacent wall, and you have light coming in, and we assume that the light projects onto the floor and onto this wall, and here we have Hopper setup, which actually doesn't work, and we're going to show that it cannot work. So let's get rid of this, and so we have the door, and I have taken this isometric setup here and I have made an orthographic setup, or if you want to call it a plan and elevation view. So this is the wall here, and this is a side view, and this is a top view. And so this red, the vertical of the door is this vertical here, and the horizontal of the door is this green line here. So the whole affair hinges on one point, this point P here, which is this vertex of the door, the top vertex further away from the adjacent wall. Everything is determined by where this point is projected, and we are assuming that for our setup the point either gets projected on this wall or on the floor. So let's treat the first case first. We assume that point P gets projected onto the wall. So it gets projected on a certain point, P prime, and we can plot this on the orthographic view. So you have the horizontal and the vertical, and here you see it on side view. And since P prime is a point of the wall, okay, then it coincides with its lateral projection. So P prime here is the same as P prime S, which is the side view of P. And since P prime is on the wall, then its top view is on this ground line that connects the wall to the floor. So you have P prime T, that is P prime seen from on top here. So now let's consider the ray of light that passes through P and goes to P prime. We can project this again in side view and on top view, and of course if L is the ray that goes from P to P prime, then its projection on side view has to go from the projection of P in side view, which is the top of the door, to the projection to the side view of P prime, and on top view from the top view of point P to the top view of point P prime. Okay, so we have this diagram. Now this determines a certain form, okay, a quadrilateral here on this view, And I put to you that every light ray must be projected inside this quadrilateral, okay? Or if you want to see it here in the isometric view, that means that every light ray has to hit either this quadrilateral or this triangle. And if you believe that, then you believe the proposition, because here you have it. It's not the form that Hopper gave you. It's a form with one quadrilateral and one triangle. Okay, this form followed from simply assuming that P prime is a point on the wall. Okay, if P prime is a point on the wall, then the rest was just orthographic projection, and it proves that this side cannot be a quadrilateral, it has to be a triangle. Okay, and now, before we prove that every spot must project onto this figure, notice that analogously, if I assume that P prime was a point on the floor, then the same reasoning would give me here a quadrilateral and here a triangle. Okay, so it would be the symmetrical setup of this, and again, it would not be Hopper's setup. And finally, there is a third case, which is that P prime could be a point on this line here, okay, on the ground line, on the folding line between the wall and the floor. And in that case, it's easy to see that this would project to the folding line, and this would also project to the folding line, and then you would have two triangular figures. Okay, so in no case do you get two quadrangular figures, as in Hopper's picture. You either get one quadrangle and one triangle, or you get two triangles. Okay, so the final step in this is just to show that indeed this figure, which has been entirely determined by the projection of P, is where all the light rays must hit. So suppose that you have a point Q anywhere on the door. Okay, so that's all the points through which light can come in. Now we are assuming that this is sunlight. Okay, so all the rays are assumed to be parallel to each other. Now look at this ray L. It determines all the others. Okay, all the others are parallel to it, including the ray through Q. Now L had a certain projection in side view and a certain projection in top view. These projections actually define two planes, a vertical plane through the ground and a plane through the wall that is orthogonal to the wall. That is, you have a plane perpendicular to the wall and a plane perpendicular to the ground, and L, the light ray through P, is actually the intersection of these two planes. Okay, so if the ray through Q is parallel to this ray L, then it must be the intersection of a plane parallel to this plane and a plane parallel to this plane, both planes passing through Q. Okay, so let's sketch this out. So there is a vertical plane passing through Q, so it's passing through the orthogonal image of Q on the ground, on the top view, and you have another plane also going through Q, which is parallel to this plane, so it projects as a line parallel to this line and going through the side view of Q. Okay, now you see that this plane hits the ground first. Okay, so when the plane hits the ground, the ray through Q also must hit the ground. So the plane hits the ground here. That defines a line perpendicular to the wall, and the light ray must be on this line. But the light ray must also be where this plane goes through the floor. So it must be at the intersection of this line with this line. And here on this view, that means that it must be on the intersection of this vertical with this line. So Q prime is here. Okay, so we have determined the image of Q prime, and here is the light ray. Okay, it goes through Q and through Q prime, and it's parallel to this one. Okay, so that's how you determine the image of any specific point. But that's not what we want. What we want is to show that whatever point I had chosen, the image would be either on this triangle or on this quadrangle. Okay, how do you show it for every point? You need an argument that works for every point. Well, and the argument is this. Look, first of all, notice that you could have the opposite of this. What happened here was that we determined which of these two lines hit the ground first. Okay, in this case it was this one, but it could have been the other way around. If Q was higher up on the door, then it could have come like this. Okay, and in this case, this line would have hit the ground first, and then to find Q, you would raise this line and it would be here. Okay, so it would be on the wall in this case and not on the ground. Okay, but the schema was always the same. You find which one of these two lines, the line on the wall, which is this one or this one, it depends on the point, or the line on the ground, hits the ground first. Okay, and whichever one hits the ground first, you do a vertical here or here, and you find the other line, and that's where the point is. Okay, but now notice this. Okay, let's go back to the initial setup. So we have these two lines. This is parallel to this, and this is parallel to this. But this one, because it comes from the door, must be parallel to this and beneath it. It has to be beneath this blue line. And this one, because it also comes from the door, must be parallel to this blue line, but above it. Okay? So in particular, this line, because it is above this line, will always hit the ground before this blue vertical here. Okay? So the point where you hit the ground must be before this vertical. Okay? And therefore, you see that the point, the actual point Q prime, must be beneath this line and beneath this line, and in particular it has to be beneath this line and above this line. Sorry, I said beneath. So point Q prime must be beneath this line and above this line, and because its top view has to project above this line, then the intersection with the ground must be to the right of this line. And so you see that point Q prime must be inside this region. Okay, because it must be beneath this one, above this one, and to the right of this one. And therefore we have proved what we wanted to prove. So let's sum this up. Hopper's setup is impossible. Why? Because, as we have shown, the whole situation is determined by the image of this point. And either the point is projected onto this wall or onto the ground. And if it's projected onto this wall, then the whole thing must project as a quadrangle here and a triangle here. Okay, or the other case is this is projected onto the floor, and therefore the whole setup must project as a quadrangle here and a triangle here. Okay, or final possibility, P projects exactly onto the folding line between the wall and the ground, and in that case the total image or the total projection of the light rays must be the union of two triangles. So it's always either one quadrangle and one triangle or two triangles. In no case can you have two quadrangles, so Hopper's case is impossible.